video, we're going to talk about cavitation. Okay, so to understand cavitation, we need to understand the meaning of the root word, which is cavity. Cavity is an empty space within an object. So you can think about cavity as air bubbles or air gaps within an object. So in this case, it's air bubbles that are formed within a fluid body. So that is cavitation. Okay, so to understand cavitation, we have to understand the concept of vapor pressure. Okay, vapor pressure is also, it can be seen as boiling pressure. Okay, so I think you are familiar with the idea of boiling water. So the pressure at which boiling happens is called vapor pressure. Okay, and as seen from this diagram, this is a phase diagram of water. Y-axis is pressure, x-axis is temperature. It shows that at different temperatures and pressures, you have different phases. Water is not always liquid. Okay, at the same pressure, if you reduce the temperature, it will turn to ice. Okay, and at the same pressure also, if you increase the temperature, it will turn into vapor. So we are very familiar with the concept of boiling. So vapor pressure is this, is when you have boiling happening, and it is the pressure that is maintained during the process of boiling. Okay, if you're confused, don't worry. Now look at this table. On your right, okay, the column on your right shows a list of pressure values. So these are all vapor pressure or boiling pressure or saturation pressure. They are all the same thing. Okay, now boiling pressure. So maybe you're not very familiar with pressure values. So look at temperature. Can you boil temperature at minus 10 degrees? The answer is yes, but it has to be at 0.26 kPa. Can you boil water at 0 degrees? Yes, at 0.61 kPa. Okay, if you are trying to boil water at 0 degrees in your kitchen, it's not going to happen. Why? Because your kitchen is 101.325 kPa. That's why we boil water at 100 degrees. Okay, in the kitchen, it's easier for us to change the temperature because you have the stove. The stove can provide heat. You can increase the temperature as much as you want. Whereas it's harder to adjust the pressure in the kitchen. Okay. So this 101.325 is actually called atmospheric pressure, standard value. It's not fixed, but it doesn't run much from this value. Okay. So at 100 degrees, this is the vapor pressure. This is the saturation pressure. This is the boiling pressure. Okay, so that is PSAT, saturation pressure, also called PV. It's the same thing. We also have saturation temperature or TSAT. Now, this is nothing new. So basically, you just change these two definition. Here is T and PSAT. You can just switch it to P, and this will be your TSAT. For example, at 100 degrees, PSAT is 101.325. At 101.325 pressure, TSAT is 100 degrees. Okay. Now let's go back to the process of cavitation to see how it's formed. Take a look at this image. Okay, so at the blade here, the blade is moving and you can see a trail of air bubbles. So how are these air bubbles formed? So basically they are formed as the blade moves. So you know that movement produces kinetic energy. So kinetic energy will reduce the pressure at that local region, not in the entire tank, but only at the trail of the blade. Okay, so this this local pressure drops below the vapor pressure. It will drop to a certain value that is lower than the PSAT that we learned earlier in the previous slide. Okay, when it drops below the PSAT, what happens is it starts to form cavities of vapor. Okay, so this is what you get. Now, as you can see, the vapor doesn't stay. The vapor disappears. So when it disappears, it means the pressure has recovered above the Pset or PV. What happens to the vapor bubbles is they collapse into liquid and then they are swept away. They're gone. Okay, they no longer exist. But in their collapse, they generate highly destructive and extremely high pressure waves. Okay, so this collapse is called cavitation. Okay, and you can't see it in this picture, but in the next one, okay, this is a clear impact of cavitation. It is a violent process that can damage machineries. So these are all caused by the collapse of these air bubbles. Okay. Now, to understand it further, you can run through this example. Please remember that all these slides are also provided as PowerPoint format, not in video. So you can always view it at your own pace if you want. Okay. So let's quickly go through this. In a water distribution system, the temperature of water is observed to be as high as 30 degrees. Okay. Determine the minimum pressure allowed to avoid cavitation. So you want to avoid cavitation and the T is 30 degrees. How to avoid cavitation? What is the pressure that determines this? Alright, so we know that the pressure that determines this is the P set at that temperature. So at 30 degrees, we find that the P set is 4.25 kPa. So in order to avoid cavitation, we must have a working pressure of anything higher than 4.25 kPa. You can operate at 10 kPa, you can operate at 50 kPa, you can operate at 100 kPa. As long as the temperature is 30 degrees, it will not cause cavitation. Okay, but if you go below 4.25, cavitation will happen. Okay, so minimum pressure to operate should be equal to the P set at 30 degrees. Very easy question. Now, how can we relate the risk of cavitation to temperature? So look at this list of temperature values. The higher the temperature, the higher the P set is. So is it harder or easier to avoid cavitation at high temperature? Right? So it is hard to avoid cavitation at high temperature because you need to operate at very high pressure as well, and it is not easy to operate at these high values of pressure, right? So there is a higher risk of cavitation in high temperature operations. So this is extra for you. You can watch this video or image here, or you can go to the slide and watch it as many times as you like, and there will be a quiz to follow up this particular image. Okay.